Okay, let's now continue with the topics about inheritance. So far we talk about inheritance being able to, by inheritance you can reuse the code from, by inheritance you can reuse the code from your ancestors, and from that we actually got lots of type checking rules. Let's just review very briefly what the type checking rules we have learned so far about assignments, about passing the method argument, and also doing cast. Okay, let's just do a review very quickly, and then we'll just talk about a little bit new topic. Okay, let's see this. In general, if I give it to you, x is assigned to y. Okay, now how do we know if this assignment here should compile or not, right? We only look at the static type. That means, what's the static type of y? Find it out in the declaration. What is the static type of x? Find it out in the declaration. And then ask the following question. Is this the descendants of that? Okay, is the static type of y a descendant of the static type of x? If it is, then yes, it compiles. Okay, that's how we see if this first category should compile or not. Okay, second one. Let's say I have a variable x over here, and then I'm trying to cast x into some class C. Remember what we said last time. Whenever you're doing cast, you temporarily change the static type of x into something. And now, changing the static type means you want to change the expectation, either to be fewer or more. In that case, you can either do upcast or downcast. Okay? So now how do we judge if this compile or not? First of all, look up again the static type of x. And then, now once you get the static type over here, you can now try to see what's the relationship between these two things. If C happens to be an ancestor class of the static type, that means we're doing upcast. We are trying to narrow down the expectation. If C happens to be a descendant class of the static type of x, that means we're doing a downcast. We are trying to widen the expectation. Okay, so now basically we are saying either ancestor or descendants, either way. Okay, now for the cast, let me say a little bit more. Let's say it compiles. But now the thing is, it's not really guaranteed to be runtime exception free, right? So now we have to also try to see if there might be some runtime class cast exception. How do we tell in this case? We have to look at this dynamic type as well, okay? So now, so green part means it compiles. Now let's look at the runtime. Runtime means I need to look at also the dynamic type of x. So the red part means I'm talking about runtime, okay? The dynamic type of x, so that means whatever C you have over here, that's the new expectation for x. In that case, if you're trying to do C that has more expectation than what this dynamic type can support, you'll get a class cast exception. Okay? So now the question you should really ask yourself is this a descendants of C? If it is, then you will be runtime class cast exception free. Okay? You got to review the lecture if you still got doubts. Okay? I'm just trying to describe from a different perspective. I'm just trying to tell you if you are the compiler, how would you judge? Okay? Okay, one more thing. Now, how do we judge things like this? Let's say I'm trying to make a method call. I say m dot, let's say object O. Okay, some object O dot method n. And then I'm trying to pass something here, I'll say x. Okay? So now, how do I know if this method call is going to compile or not? So there are several things you have to look at. Two things, okay? So now, first of all, you want to know if the method over here is really supported by the static type of O, right? For example, if you try to do premium rates, but the static type is actually students, in that case, it's not supported, right? So now, first of all, number one, look at the static type of O, and then ask yourself if n is defined or not. That's the first part, okay? Now the second part is, what about this part over here? I'm trying to call this method here, right? So now, once you find out the method m is defined in the static type of O, you can go to that definition there and see what's the parameter type. Remember we talked about parameter there. The parameter type is a static type you're trying to assign into. In that case, you have to look at what's the static type of X. And then this should be, is that a descendant of the parameter? Okay, in that case, you got to see what's the corresponding declaration for n. Okay, that's also something we talked about last time. For example, if you say add resident students, in which case the add resident student has the declaration of resident students as a parameter type. Now, if you try to add something which is of static type students, in that case you cannot add it in because student is not a descendant of resident students. Okay, you can also review the slides about that part. Any question about these three? I'm just summarizing what we have done. Yes. Oh, context object, just O. Just O, yeah, just object O. Yeah. Just in general. So you will see that at the end of the slides, I actually got a huge table over there where you can actually see all the type checking rule we have introduced. Okay, we'll go there. Okay, guys, let's now go a little bit further. So this is what we left from on Tuesday, last Thursday. Okay, so now let's go a little bit further. Let's just do some case study very quickly. I'll just do one with you, and then you can do the other two quite similarly. So now, I want you to look at line number 1, actually, line 1, 2, 3, and 4. Let's go over one by one. In line number 1, we declare S to be of static type students. The dynamic type happens to be student as well. Okay. Line number 3, we're trying to create an empty student management system. Okay. Now in line number 4, does it compile? Okay, let me give you a little bit hints. If you want to see if the compiles are two things, is addRS a method that's defined in the static type of SMS, which is student management system? Do we have that method there? We do, right? Let's go there. Okay, I'll just show you. If you go there, we do have addRS over here, right? So that's exactly over here. Okay, we do have that method there, so you can call that. Now, second step, what's the static type of the parameter? It's resident students. Okay, let's keep that in mind. And now let's go back to that original line. It's resident students. Now we are trying to pass an argument whose static type is actually students. Now ask the second question. Is students, the argument static type, a descendant class of the parameter static type? Is it? No, because student is not a descendant class of resident students, so no. Now, okay, so far so good. Now, what I can do to trick the compiler is I can say I want to temporarily change the static type of S. So now in this case, I know that to make addRS happy, I can just cast anything into students. It's an upcast, right? From resident students into up to students, right? You can see S, this static type used to be over here, students. Now I can actually downcast, sorry, let me say that again. I can downcast because you can see the students, the S over here, the static type is students. It does not make the addRS happy. So what I can do is I can do downcast. I can downcast students into resident students, like what I did do over here. Okay, you can see what I'm doing here, right? Now, this one doesn't compile though. Think about it. Let's break it down. Okay, I'll show it to you. Okay, let me just first of all write something on my iPad and I'll show you. Okay, let me just give me 10 seconds. It's really important to understand this line. You kind of combine all our knowledge from before all together. Okay, and then, yeah, I know, it's intentional. I'm just trying to put everything you need. Okay, let's look at the iPad over here. Now, and so this is what we have, and then we know that, first of all, in the class student management system, right? And then we have the method addRS. Over here, we have resident student as a static type, and then some RS. Okay, and then we got something here. That's all you need to judge. Okay, let's do it from scratch once more. Okay, now let's break it down into two parts. Actually, in this case, there'll be 3 parts. First of all, this part over here, part 1. Does it compile? We know it does because static type for SMS is SMS. which is over here. That one does have this method here that's defined. So this part is okay. We're calling some known method to the static type. Okay. Step number 2. Does this class pass or not? Okay, let's try. Again, static type of S, we know that it's students. Okay, let's put student over here. And then, in this case, are we doing downcasting or upcasting? Downcasting, right? Because resident students is a descending class of students, right? So now that means this is, so now we know that we're doing downcasting. Now, final step. Let's say once we got this expression over here, let me just highlight it like that. Once we get this one here, the green part, what's the static type of this particular expression here? Resident student, right? Because we temporarily changed that to be resident students. Now, we want to know if this highlighted green part can be passed as argument for @rs. Now, we should be able to, right? Because now we know that, let me just write it again. So now we know that this part over here, the static type, I'll say temporary static type, is actually resident students because we have done a cast, right? And then RS is actually a descendant class of the parameter type. It's a descendants. Okay, so everything pass. Huh? Yep, let's don't only talk about compilation. We'll worry about runtime in the next step. Okay, now so for the green part, we only worry about runtime only. Okay? Guys, are we okay so far? Okay, so you can see there are 3 steps you need. Okay, in the table at the end of the slides, I also summarize it. Okay, now next question. Is this code going to run okay at the runtime? So now to really see if that runs okay at the runtime, we have to bring dynamic type into the context. Okay, let's go back to the slide here. You can see the dynamic type of student S is actually new student. Let me add it to the context. Okay, now it compiles, but I'm going to put new over here, students. So now let's analyze the runtime behavior. Okay, so now basically you can see particularly when we are doing this particular cast, when we say RS and then S, okay, over here, we're doing this cast. Now, if you want to know if a cast compiles, we have done that already. Now, we want to know if this cast over here is going to throw class cast exception. Okay, let's look at dynamic type. What's the dynamic type for S? Students, okay? Student over here. And now, you can see that the actual dynamic type is actually students, but we are trying to use the expectation of RS on that. Are we going to run into trouble though? We are, right? Because what's the expectation for RS? Premium rate, for example. A premium rate is not really available on the students. Okay? So basically the question you're going to ask yourself is this student class a descendant of RS? No? So that means we got class cast exception. Okay, any question about this? Yes?
So the list is of type student.
Yeah.
And you're adding RS, the parameter RS into the list of students. So
Uh-huh.
there will be no error.
No, there wouldn't be any error. So let me make it clear. Okay, let me just go back to what we said on last Thursday very quickly. So now let's just have a look at this over here. Okay, for example, over here, you can see we are calling the same method over here and RS. What's the dynamic type for RS in this case? You can see it's resident students, so that's fine. No cast is needed because you can see, first of all, the static type for RS over here, which is resident students, it is a descendant class of the parameter type, which is resident students. And then at the runtime, you're really pointing to your resident student objects, so you don't have any class casting. Yeah. The iPad or just a class? You mean here? The class, SMS, okay. Which method are you talking about?
Add RS.
Add RS, okay.
compile the line 3, SSC is equal to RS because the dynamic type of SS is...
No, when you talk about compilation, you only worry about static type. Okay, right? Yeah.
So the static type of SS is student and the dynamic type of RS is also student.
No, again, you don't talk about dynamic type when you talk about compilation, right? So now, this line over here compiles because the static type of the right-hand side, which is RS, the static type is resident students, okay? And what's the static type for SS at position C? Also students. So resident student is a descendant class of students. So when you talk about compilation, you never talk about dynamic type. It's only when you want to know, for example, if there will be any runtime class cast exception that you will talk about dynamic type. Yeah. Okay. Guys, any questions about this? Yes?
Just quickly repeat on the iPad.
Yes.
Why it would have a runtime exception.
No worries. Yeah, of course I can. Okay, let me just make it a little bit cleaner. I think it's really important, okay? Because I really want to ask you about this in the final. Oh, hey. Guys, by the way, most likely I'm gonna write an exam for your section, most likely, okay? And I'm not too sure about the format just yet. I will give you definite answer either Thursday or I'll write you an email. And then I'm gonna have extended office hour next week, so you can always come by, okay? But you're under my full control for the final exam. Okay. I believe for section E and section B, they're gonna write a common exam, but our section I'm gonna write different. Because I believe they write kind of they're gonna use the same slides, materials, but we kind of use only mine. So it will make more sense if you write my own exam. But if you really insist to write other sections exam, please feel free. But that's fine, I'm not offended by that, okay. Okay, let's repeat this once more, okay. Okay, we got SMS dot add RS over here, and then let me just remind myself quickly, and then we got RS. Okay, S over here. Okay, and then over here we say students over here, S is assigned to new students. Okay, now let's analyze the runtime behavior. Whenever you talk about runtime behavior, you have to look at this dynamic type. In this case, students. Okay? Now, let's look at this particular cast over here. What does that mean? That means we want to cast S to RS so that we can apply the expectation on of RS on S. And here, what particular expectation I'm talking about? For example, premium rates. Right? Because we know that for the resident students, the very unique feature, unique attributes we have is premium rates. Now the thing is, when we call S.PR, is it gonna be okay though? Nope, because student object here has no premium rates, okay? We know that, so cannot meet this expectation. You will compile, but we will run into trouble. As I said before, the compiler is very naive, so you can easily trick the compiler. That's why, to really avoid such trouble over here, you better do some instance of check before you do it, okay? So now, cannot meet expectations, so you got class cast exception. Okay? What would be the expectation we can do? Yes, but you know what? If you simply do this, you're gonna run into trouble anyway. So now, what you can do is, you know what? Just for this example here, are you okay? Yeah. Okay, yeah. So I would say go over the other two examples, it will show you. Okay, yeah. Guys, any questions before I leave you with the other two examples? They are very similar, okay? Okay, that's the first one. So what should you do, basically? You should really do instance of check. Okay, let me show you over here. What you should do is, you should do instance of check to say, S is really, the dynamic type is really something you can expect from for resident student, right? Remember we said before, when you do this check instance of, what does that mean? You're checking that the dynamic type of S, which is students, is it a descendant class of resident students? It is not. So it's going to be false. You're going to bypass this cast. Okay, good. Okay, I got another 2 examples over here. You can just go over them and follow the same reasoning. Okay, I'll leave them to you. Okay, one more thing. Let's say we have this over here. Let's say we are trying to say add RS and then we pass NRS. NRS is of static type non-resident students. We know that it wouldn't compile because non-resident student is not a descendant class of resident students. Okay? Now, do you think this will compile though? Just a quick check. Do you think this cast will compile? Yes? No? No, why not? Exactly. You're neither doing upcasting nor downcasting. Exactly. Whenever you do casting, either upwards or downwards. That's the principle. Okay, this one is neither. Okay. Raymond, okay? Good. Okay, very good. So now let's talk about something about return value very quickly. So we have covered method arguments quite thoroughly. So now you should really be able to judge, whenever you want to do to see if one line of method call should compile or not. Okay, let's do this one also thoroughly. Let's talk about return values. Let's say in the student management system over here, again, we got a student array. So the static type of each element in the array is students. And then let's say, we still got as students over here, right? The static type is students, okay? Now, let's say we define a new method, a accessor. And we say get students. I want to say in the array, I want to get the student at a particular position, right? If I say integer I being 0, I want to get the first student in the system. If the integer I is 1, I'll get the second student in the system. Okay? So now, let's say this is how I do it. I simply say student, so it just corresponds to the return type. So say students. Okay? So this is something I'm going to return as return value. And then I would say, if somehow the index is not valid, I'll throw illegal argument exception. Girls? Okay, so now we would say that if the integer index is not valid, we're going to throw new illegal argument exception. Okay. Otherwise, we simply say S is assigned to SS at position I. Now, tell me something. Is line number 10 going to compile? Line number 10. Okay, let's think about what's the static type on the right-hand side. Should be student, right? Because any element in the SS array should be static type students. And then what's the static type of S over here? Students, right? So it compiles. Very good. So far, so good. Okay, and then we simply return S over here. Okay, nothing special here. Okay, now this is an important question. At the runtime, if I simply return something from the array, what can be the dynamic type of the object I'm returning? It can be any of the descendant classes of the student class. Okay, let's see how this happens first. Okay, the intuition is simple. Thinking this way, we know that we can pass any arguments whose static type is a descendant class of students, right? That's what we learned from before. Now, what are the descendant classes of student? We got students, we got resident student, we got non-resident students. Those are the objects we can store into this array. Okay, let's see how that's gonna occur. And now I'll draw you some diagram. Okay, so now what's the dynamic type of S after line 10 in this case, right? It can be all the descendant classes, but let's see how. Okay, let's try. So again, let's try this. We say we have a course over here, 2030, and then we got RS dynamic. You can now see that what I'm really concerned about here is the dynamic type. Okay, compilation is not really the issue. Okay, so now let's say RS dynamic type is resident students. Okay, and then set the premium rate to be 1.5 and register 2030. Okay. Also, we got another object called MRS, and then the dynamic type is non-resident students, and that means we got discount rate. Okay, so we got two student objects. One is resident students, the other one is non-resident students. Dynamic type are different. Now, let's say this. Line number 6, we create an empty student management system. Line number 7, let's try to see what's going on over here. Okay, I'm going to draw you some diagram. Okay. Okay, first of all, let's try this. We have SMS, which is a student management system. And then we know that one of the attributes is SS array. Okay, let's make sure we understand what a static type is. We know that it's actually students array. So that means every element in the array is of static type students. Okay, let's get it clear. Okay, and then we know that there's going to be an array, okay, of this certain length. Okay, 1, 2, 3, all the way to the end. Okay, now let's try the first adding. We say that SMS is a add student RS. So what does that do? Okay, let me just write it here. When I say SMS dot add RS, let me just make sure I did it right. Add students, beg your pardon. Add students. And then RS. Okay, let's see what RS is. RS is a resident students ratio. Let's draw it in the diagram first. So RS is somehow we created a student object from previous code, RS, and then we have name. We have also premium rates, which we set it to be 1.5. Okay, and this is ratio. Okay, so now let's think about what this line would do. If you look at the definition for the add students, you can see that, I'm just showing you very quickly. You can see that it's simply going to be SS at position C. C is a counter of how many students we have got so far. It's assigned to S. Okay, so what we will do over here is we're going to say SMS dot SS at position 0 because currently there's no student just yet. It's assigned to RS. That's the first line. So what does it do? Well, it's going to somehow point this over here, right? As we did before, okay? And then let's go there, go to the next one. What about here, SMS.addStudentsNRS? It's going to be something very similar, right? Except that now count has been incremented from 0 to 1. So now what we're going to have is, we have, let me just draw it here. We also got another student object over here, NRS, over here. And then we have NRS, and then we have name, and we have the discount rate. I believe 0.5. You can check in the code. And this one is Nancy. Okay, Nancy, I'll put N here. Okay, and then after saying SMS dot add students, the same method, but now we try to add NRS. Okay, you boil it down into SMS dot SS at position 1. And then it's assigned to NRS. That's what we'll do. Agree? Now, that means this part here is going to point to here. Okay? So far, so good? Okay, now here is a remark I would like to make. That's why I want to draw the diagram to show you. First of all, again, remind you about the static type for each element in the array is students. It doesn't change. However, what's the dynamic type? Dynamic type, remember what I said in the previous slides. Look at the title of the box. Okay? That means the dynamic type of the first element in the array is different from the dynamic type of the second element in the array. But their static type is the same. Okay? Guys, follow? Okay, good. Now, let's try this. If I say this, let me do some instance of check for you. If I say SS, oh, let me just do one thing, and now let's say, I'll get to here. So let's consider this line over here, okay? Let me write it on my iPad and then I'll show you. Okay, I can say student is assigned to SMS dot get students at position 0, okay? Okay, this is a line I want you to look at. This is a line, okay? This line here, okay? Now, first of all, does this line compile? Okay, now I want you to look at this is an assignment over here, right? Why does this compile though? what's the static type of the right-hand side? Static type. I'll give you a hint. Why don't we go back to the code and tell me which line can you infer that the static type for the right-hand side in this assignment here is something? How do you know? Which line? Line 3, line 2, really? Line 5? Line 0? Wow, amazingly, you haven't got the right answer yet. Huh? Say that again?
Line 2 assigns everything in the array to a static type.
Okay, you're getting a little bit too complicated. Thinking this way. When I look at the right-hand side, this is the right-hand side, right? The right-hand side is a method call, right? This method call here, which method are we calling? Get students. How do we know the static type of get resident students? Oh, sorry, get students. How do we know? Yeah, that's the type, the return type of this method, right? Yeah. Line 4. Nobody said that, right? You said that? Oh, sorry. Didn't hear that. Yeah, it's highlighted. Yeah, exactly. Yeah, it's even highlighted. Yeah. Okay. So, okay, let me go back there and then tell you that the right-hand side over here, the static type of this is the return type of, I'll put it here, I don't have space, of get students. In this case, let me just also make a connection, it's line number 4. Okay, guys, follow? So that's how I reasoned about it. The right-hand side for this assignment here, I'm trying to make a method called get students. And get students, as I can see from line number 4 in the previous slides, it declared the return type to be students. That means anything I return, the static type is going to be students for sure. Dynamic type, it can be any descendant classes of that. Okay?
In line 4,
Yeah.
we couldn't put resident students.
That would be changing the whole story, of course. I'm just saying, in this case, we just make it students. Yeah. Let's say hypothetically, if you change line number 4 to be simply just resident students, okay? In that case, things will get a little bit more complicated. I wouldn't want to get into. Just leave it there. Okay. Okay. Any questions? Are we okay? Now, we know that the right-hand side has a static type, which is students. And then is students a descendant class of students? Yes. So this will compile. Okay, so now, however, thinking this way, if we say that, I want to again draw your attention to this assignment over here. So now, when we say S is assigned to this, so now let's say S is over here. Which object is S going to point to? Let's review very quickly over here. You can see to say get students I, I'm simply going to retrieve whatever student object it is at position I, right? In that case, I'm going to get this one, right? Okay, so that means S is going to point to this object over here, okay? Now, what's the dynamic type for S? Resident students, agree? This is a little bit sophisticated. Do you want me to repeat or you're okay? You're okay, right? Okay, yeah. If you want me to repeat, either watch a recording or come to my office hour, either way. Okay. Yeah. Okay, now, so line number 8, I also put some annotation for you over there so you can just follow, okay? And now let's try this. Given that the return value from SMS.getStudent is 0, we know that it's going to return this object over here again. That object has the dynamic type resident students. Now, when we say as instance of students and as instance of resident student, is it going to be true or false? True, false, okay. Yeah, they can be that third possibility, right? So now, think about what's the dynamic type for S. What's the dynamic type? Resident students, good. What does instance of do? It's gonna check if the dynamic types of S, which is resident students, is that a descendant class of the class we are checking? So resident students is a descending class of students. Resident student is also a descending class of resident students. True. What about here? False, right? Now, the same dynamic type, resident students, but resident student is not a descending class of non-resident students. Okay, it's gonna be false. Guys, any questions? Are we okay, right? Now, of course, now if you say get tuition, so now which version are we going to call? It's going to be the version in resident students, non-resident students, or students. Resident student, dynamic binding, okay? Don't forget, okay? So everything connected together, okay? Good. So now you can do similar reasoning over here. Now I say that, oh, I think this is typo. I'll fix that. It's very important. So sorry, otherwise things wouldn't work. This should be index 1. Okay, it should be 1. So now if I say SMS.getStudents 1, okay, so this one over here, would it compile? Compilation. Compilation only considers static type. Again, this right-hand side, static type is students. Student is a resident student's descendant. Is that right? Nope. Nope, doesn't compile. Okay, good. Okay, and then you can do similar reasoning here. Now, let's say I pass 1 over here. Now, SMS.getStudent1. So now what I will retrieve is this object over here instead at position 1. Now, the dynamic type is now not resident student, but non-resident students. Right? Over here, you can see that the dynamic type is non-resident students. Okay. Now, in this case, you can do also instance of check. Okay. Now, you can just say it's a non-resident student, of course, instance of non-resident student, right? Okay. You can just follow the rest. Okay. Any questions? You can see there are many bits and pieces that you have to know in order to understand this fragment of code. It's really important. It really summarizes what we have learned so far. It's really important. Questions or? Okay. I would suggest so, yes. So anything I give to you in the exam, it's going to be very similar to the exercise we did last time. We remember symbolic, A, B, C, D, E. So you really want to draw some hierarchy there and then kind of remember what the rules are. Yeah. Okay, so now let me, one more thing to say about this example here. We say that at the runtime attribute SMS.ss is called a polymorphic array. What do I mean? Basically, you can see the static type is students. However, the shape of each element can be different. It can be a resident students, it can be non-resident students. So it's polymorphic array. Okay, that's just some terminology. And then you can see the diagram as well. Okay, basically what I draw over here, the same. Okay. Okay, one more. Let me just go back here. So why do we need inheritance? Let's go back to where we were about a week ago when we first introduced inheritance. We want to have a collection of different kinds of students. If we did not have inheritance, we would have declared an array for each kind of students because the resident student class and non-resident student class without inheritance have nothing to do with each other. Okay? Now that we got polymorphism and inheritance, everything will work just smoothly. Let's see very quickly. So now let's say we got student management system here. Now we can declare students to be of static type students over here, right? That means any students of descending class of student, we can put them in, okay? And then we got add student here, and also register all. So you can see we have some common codes to register. Now a single loop will just do rather than multiple loops, as we said before. So now we can simply just go over this array and then say this. Now think about this. This line over here, when we say students at position I that registers C, okay? At the runtime, how is dynamic binding going to work? As we said before, the array is like a polymorphic array. That means the dynamic type is going to be any descendant class of students. In that case, if position I happens to be a resident student's dynamic type, that means it's going to call the register method from the version in resident students. Otherwise, it's going to be another class, right? So that's how dynamic type binding works. Okay, so now you can also go over another example here. Okay, just depending on what student you add into the system, when you call get tuition, it's gonna give you a different version of the get tuition, right? Okay, so now you can see Jim over here is of dynamic type resident students, and Jeremy is of dynamic type non-resident students. So when you actually call the same get tuition method, it's gonna make difference, right? One is gonna apply the discount rate, the other one is gonna apply the premium rates. Okay. Now, when to consider which? Let's summarize. Okay, almost getting to the end. Now, when to consider which? Again, if you only want to know if your Java code compiles or not, static type only. Don't even bother to think about dynamic type. And then, if you want to somehow analyze the behavior of your Java code, you may have to consider dynamic type. For example, if I know that the class cast compiles, is there going to be some class cast exception at the runtime? I need to look at the dynamic type as well. Okay, you can also read the paragraph. I don't need to repeat. Okay, the best practice is for you to draw diagrams, really, like what I did in the class. Okay, okay, so there, over here, this table here summarizes all the type checking rules we have covered. Okay, don't memorize them. Try to see if you can really try to understand by your heart, so you can memorize them very naturally, right? Or just remember them. I may allow some data sheets for the final exam, in which case you can just put them in. I will tell you if I will allow or not. Okay, so you can just go over them. That's exactly how I summarize this in the very beginning of the lecture. Okay, that's on the table you can go through. Okay. Now, one more thing before we conclude the inheritance, and then I'll move on to the new topic. Okay, so now let's talk about overriding and dynamic binding. Okay, let me just give you an example right away before I go through the slides. Okay, let's just give you one example to compare. Let's say, remember we said before, every class has the superclass being objects, right? Let's say we have a situation like this. B extends A, C extends B. Of course, every class implicitly extends objects, right? Let's just make it simple. So in some way you can see A also extends object, right? You can think of objects at the top, okay? And then let's just take one example. Let's say the equals method. At the object level is simply going to compare the references, right? As we learned before. Now, question for you. Let's say, so that's exactly what we got. You can see in the class A, we do not try to override the equals method. In class B, we also do not try to do it. In class C, we also didn't try to do it. Now, let's say the following code. We have object C1 is assigned to new C. Why would this compile? Because C is a descendant class of object, right? And also we got object C2 is assigned to new C. Now, when I say print line C1 dot equals C2 over here, false. Tell me something, which version is it going to call? On the object, right? You can see basically at every level of the hierarchy here, I'm not trying to redefine. I'm not trying to override. Okay? In this case, object. This case is easy. Let's see the second case. The second case over here, let's say we do try to redefine only at the bottom level over here. Only that. Okay? We do something there. Doesn't matter what you do. Doesn't matter. Now, again, you can see the class structure over here. B extends A and C extends B and overrides equals method. Now, the same block of code. When I try to execute line number 3, which version of equals am I going to call? From object or from C itself or from B or from A? From C, right? Again, think about dynamic binding when I ask you about which version. The dynamic type for C1 is C. And then you kind of see if the current class of the dynamic type has the equals method redefined. If it does, call that. If it does not, the principle is you got to look for the closest ancestor which has redefined that. You got to go all the way up to the hierarchy. In the first case, because we know that C does not define that, go to B. It does not go to A. It does not go all the way to the objects. You got at least one version that's defined there. Yeah.
So to clarify, let's say the change is up, let's say B has
Okay, we'll get there. Exactly. That's exactly the next one. Good, good. Okay, let's go to the final example there. Okay. Now, let's see this. Okay. It's exactly what you meant. Okay, now, you know what? I think there's a typo there. I meant to wipe out this version over here. Okay. Okay. That's what I meant to do. Okay. Okay, let's say this. Also, this one should be white. So now look at the code. The code is right. Let's say B extends A. In B, we try to override the equals method. But in class C, we extend B, but we did not try to override the version. So now we got, how many versions of equals do we have so far? Two, right? First version in the object class. Second version in here. Again, this is typo. Okay, I'm going to fix that. Now, line number 3. Which version are we going to call? Objects or B? Remember the principle, the closest ancestor that has redefined the feature or the method, right? B. Okay? If you see the diagram, it's very easy to understand. Okay, B, closest ancestor, yes.
Will that give you the right answer?
Huh?
Will that give you the right answer?
It depends. So again, whether to override the equals method at this particular class is completely up to you. If you think that's necessary, do it. Okay? If it doesn't do what you want, do it in another class. Okay? I'm just trying to show you if this is what it is, then that's what you will call. Okay, I'm going to fix this typo here, and then the slides with the bullet point here simply tells you all the 3 cases. You can read them over. I don't need to repeat. Okay, this is the last slide for inheritance. Do you have any questions for me? Questions? Are we okay? If no question, I'll move on to the next topic. Okay? Next topic, you will see. Exciting topic. Very exciting. Okay, now, let's go to the next topic. I'll show you. When you see the slide title, you will see. Let me just close that first. Okay? Okay, it's called abstract classes in interfaces. So there are 2 concepts, actually, and they are not that difficult. The way I would like to show you is, I want to show you maybe just by examples, and then at the end, I will give you some principle about when to use abstract classes and when to use interfaces. They might seem a little bit similar to you at the first, but they're quite different, okay? So I'm going to show you 2 typical problems for each one of them, okay? I'll see how far we can go. Hopefully, at least we can finish the abstract classes today, okay? Because after this, I do have one more topic I would like to cover before say goodbye, right? Okay. Now, let's talk about abstract classes. I want you to spend just 1 minute for me, just read through the problem, and then I'm going to summarize at the end. Just read through it very quickly, okay? Okay, everybody got a chance to read it? Okay. Now, let me just try to summarize for you. First of all, you can see that there are 3, the empty bullet points over there. So these are the 3 methods we would like to support. The first one, we want to grow the polygon, right? Either can be a triangle or a rectangle. So these are the 2 special cases. And the second one is, we want to compute its parameter. And the third is, we want to compute its area. Now, for number 1, it's kind of not quite easy. Let's focus on number 2 and number 3. Okay. Now, if I want to compute the parameter for triangle and rectangle, can I find a uniform formula for that? Triangle and rectangle to calculate a parameter. Okay. If you know what parameter is, right? Okay. That's really important. Okay. Again. Now, let's say I got rectangle over here. I got A, B, C, D. And then I got triangle over here. So I have, let's say, E, F, and G, right? So, parameter. So now how do I get, oh, maybe what I meant to say was circumference. not really parameter. I always got these two words confused. So I really mean the sum of all the sides. That should be circumference, right?
They're actually the same.
They're the same thing, right?
Circumference is for a circle.
Ah.
The parameter for a circle.
Okay, anyway. Let's say parameter for polygon. How about that? Okay, good. Okay, let's not worry about that. Okay, at least I didn't get anything terribly wrong. Okay, let's not worry. Let's say we try to work out the parameter, okay, over here. Now, is there a uniform formula for me to calculate the parameter? In the case of rectangle, a plus b plus c plus d. In this case, e plus g plus f. Well, EFG, of course. Yeah. There's a uniform formula for this, actually. How? Think of, as a polygon, you can think of rectangle has 4 sides. For triangle, you got 3 sides. What we can do is we can declare an attribute for both, just call it sides. Integer array sides. In the case of the rectangle, it's going to be of size 4. In the case of triangle, it's going to be of size 3. But how do we have a uniform formula to calculate the parameter? Well, why don't you just run a loop, right? In the case of the rectangle, you run 4 iterations. In the case of the triangle, you run 3 iterations, right? So you do have a uniform formula for that, right? That's what I meant. Now, let's go back to the original problem here. So the conclusion is for parameter, you do have a uniform way to actually calculate the parameter. That means the code you have for calculating the parameter does not have to reside on the rectangle and triangle. We'll see. Okay. Now, one more thing, which is about the area over here. How do we calculate the area? In the case of the rectangle, we're going to do basically a times d, for example, right? Width times length. But can we do the same formula to calculate the area for triangle in general? No, you cannot. However, fortunately, there is a formula over here. It's called Heron's formula. You can look it up. Okay, you don't have to memorize it. Okay, you can see Wikipedia. And there's a Heron's formula, which means given the sides for any triangle A, B, and C, the sides, this is how it calculates area. Apparently, this is a formula that cannot be shared by rectangle. You cannot do the same thing for rectangle, of course, right? So now, how do we solve this problem here, right? We want to support all the 3 functionality over here: grow the shape, compute the parameter, and return its area. And then somehow we know that parameter can be done by a uniform formula, but not the case for area. How do we do it? Okay, this is a very typical problem for abstract class. Okay, I'll describe to you conceptually, and then the rest will be quite easy. Okay, let me just tell you what the idea is. First of all, we got a superclass polygon, and then we're going to get 2 subclasses. And then we got triangle, and then we have rectangle. Okay, let's now focus on the 2 methods we want to support. Okay, first of all, what we can do is, because the polygon is a superclass, so we can declare whatever that can be shared by all the descending classes in the superclass. It's a code reuse, right? So now what we can do is we can say integer array and then sides. Okay, that's what we can do. So that means triangle has an array of sides of size 3, and rectangle also have an array of sides also of size 4, right? Now, let's talk about the 2 methods. Let's say we want to have a method. I'll just put integer for simplicity. One is get parameter, and then we also got another one called get area. Okay, now these methods are somehow belonging to different categories. As we said informally before, the get area method, in some way we cannot define at the polygon level. Because at the polygon level, we simply don't know, are we a triangle or are we a rectangle? Depending on which shape you are, you're going to use a different formula to calculate the area. On the other hand, for get parameter, you can have a common definition for all the descending classes. How do you do it? Just run a loop and sum up all the sides, right? So now, conceptually, that's how you can think of it. So now I'm just going to say you can define this, get parameter over here. I'll say sum up the size. Okay. On the other hand, for this one over here, get area. So we're going to make it undefined at this level. So there is a way to do this. I'm going to put a star over here, which means we're going to make this method over here abstract. So this is something new to you. So far, you can never leave a method simply just empty. You wouldn't get any useful things from that. However, from the modeling or design point of view, at the superclass, you may want to make some methods abstract, simply because at a superclass level, you simply have no idea how to define that just yet. Okay? So if we make this abstract, that means at a triangle class, we're going to say integer get area. We're going to define that over here. And then we can simply apply Heron's formula. Okay, that's one. And then we can also do in a rectangle class, integer get area. So that's going to be a different formula we're going to apply. You can simply say, width multiplied by length. Okay. Girls, I can hear you very clearly. Okay. Now, let's any question about this conceptual ideas over here about abstract classes. Okay. Again, you can see that over here we are trying to say for this method here, we simply cannot give you a definite answer at the polygon level. However, at the descending classes level, we're going to give you a definite answer. Okay? Yes? In this case, you know what? Let me make that remark maybe at the end. Let's just continue with this example. Yeah. So the question was, could we actually have made the student class abstract? Okay, I will get to that. Okay. If you have no question about this idea, let's go over the syntax, how you can do it. Okay. Hopefully, once you see the code, you can see exactly how it can be done. Okay. Now, first of all, we declare polygon to be an abstract class. Usually, when you declare a class to be abstract, that means you want to have at least one method unimplemented. Unimplemented method means it's abstract, okay, as opposed to concrete. Okay, let's see that. Okay, we declare size, an array of double or integer, doesn't matter. And then we have a constructor over here. So now we can say that just assign the size. Okay, you will see how it is done. By the way, the sample code is also available in the website. You should really play with them, okay, and have a look. Now we can try to grow. When we try to grow, we simply say increment each side. Okay, so maybe you used to have 2 by 3 rectangle. Now it can become 3 by 4. Okay, something like that. And then get parameter. That's, as I said before, you can have a uniform formula for calculating the size for all the descending classes. You simply just sum up the size. Okay, and then return. Okay. This one here is really interesting. Let's have a look at this. This might be something you haven't done before. Let's look at the last line. First of all, we declare this method to be abstract, okay? And we have the return type. And then we have the method empty parameter list. And then we don't have the curly brackets that we usually have. We just have a semicolon, okay? So over here, we are declaring only the signature of the method without giving any implementation body. Okay? So now what does that mean? That means for this particular class, we simply just want to leave this method here unimplemented. Okay? If you leave that unimplemented, that means any descending class who inherits from this class, they should try to implement this method over here. For example, rectangle or triangle. Okay? Let's look at that. Okay, signature only. And then this is a very important thing to notice. I'm going to show you. Okay, let's say we simply have class polygon over here. Remember, that's abstract. Okay, I'm going to show you over here. So now let's say here we say polygon over here, and then P is assigned to new polygon. Like that. Okay. Now remember that what we declared was abstract class polygon. That's what we declared before, right? That's what we did before, and something like that. So now, if you try this line in Java, it's not going to compile. Okay? Over here, we're saying that we are using abstract class Polygon as a static type. And we're also trying to use the same class for dynamic type. Okay? What's really wrong over here is you cannot use an abstract class as dynamic type. That's really the problem is. Okay? So now the issue is you cannot use abstract class as dynamic type. Okay? It simply wouldn't compile. But let's see some intuition why this wouldn't compile. Okay? Let's try the following. Again, proof by contradiction. Very easy. Very easy. Let's say hypothetically, if I allow this line to compile, what's going to happen if I say p dot get area? Wow, is it going to call anything? Look at what we had before. Where is the definition for get area from Polygon? Well, nothing here, right? Only signature. So now if you try to call that, it's pretty much like division by 0, a little bit like undefined, the result. Okay? So that's why crash, because it's undefined. Okay? So now the lesson is you can never use the abstract class as dynamic type because at least one method over there is undefined, at least. However, you can use it as a static type, which we'll see for polymorphism. It's actually quite recommended. So let's say we got polygon here. What can be the dynamic type? It's a preview. It can be rectangle or it can be triangle. When you say, when the dynamic type happen to be rectangle, when you say p.getArea, it's going to call the formula for rectangle. When the dynamic type happen to be, let's say, triangle, in that case, p.getArea is going to apply the Heron's formula. Okay? Any question about this? It's very important. Okay. Okay, let's now go back there and then try to do a little bit more. Okay, let's say we got everything else is pretty much the same. So now we say class rectangle extends polygon. So now you got two options for rectangle. Because we know that it's going to inherit everything, especially the abstract method, which is getArea from the polygon class. Now, the rectangle class has two options. You can choose either to implement that getArea method, or you can choose not to do it. If it chooses not to do it, that means this class has to be abstract as well, because it got at least one method that's abstract, right? So now, let's say we choose to implement that. Okay, that's what we want to do. So what you can do is, for example, you can see the constructor over here. You can simply say, you got 4 sides, right? If I give you the length and the width, I can simply assign each one of them. Okay, you can go over the details. And then we don't have to redefine, remember we also inherit get parameter and also grow. Now the only thing we add is get area. Now we can simply say the first side multiply the second side, the width multiply the length. Okay, that's the definition. Okay, any question about this? Yes. Yes, you may. Yeah. So it's you know what? Since we say extends, so everything that we said before about inheritance still apply. The only thing is, in the abstract class, you got at least one method that's undefined. In that case, in the descending class, usually you got 2 options. You can choose either to put the implementation for that undefined method, or you can choose not to do it. Okay. Yeah. Good question. Let's say we do this. Let's say we try a little bit different design. Let's try. Let's say you got polygon over here. Okay, we still got rectangle and we got triangle. Let's say over here we still got our integer array, the sides. Okay. Okay, I believe what you're suggesting was, let's say we don't want to declare any abstract method. So let's say we put the get area in the rectangle and triangle instead. Okay. Let's say we put the get area over here, and then we're gonna apply something over here. And also we got get area method over here, and then we do something over here, the Heron's formula. Okay, so you can see now for polygon, we have no get area method. So now, let's say this is what I want to do. I want to create something like an array of polygon. I want to collect different kinds of polygon. Pretty much like in the student management system, I want to collect different kinds of students, right? Resident students and non-resident students. Now I want to do the same thing. I want to collect rectangle and triangle, okay? So now if I do the following, let's say I have a class over here that's called a polygon collector. Actually, you will see that in just a moment, but let's try to do that, okay? So now I'm gonna show you how this is gonna run into trouble, okay? If I say polygon collector, okay? Now, let's say we say polygon over here, and then I'll say PS, polygons, okay? Now, let's say over here, how do I find out the area? Let's say I simply got something like this. Let's say void. I'll simply say print areas of all the things in the polygon collector, right? Which can be rectangle, which can be triangle as well. Okay? Now I simply say, okay, put it here. Okay? I'll say for whatever over here. And then I'll say polygons array at index I, which is loop counter. And then I say get area. Do you think this is going to work? Is it even going to compile? The answer is it's not going to compile. Why not? Okay, again, to see if this method call is going to compile, we're going to apply what we learned before. Okay, first of all, what's the static type for this? Static type? Polygon. Does polygon define the get area method? Nope. So it doesn't compile. So now in your design, which is okay, what you gotta do is the small version, which means we have to declare one array for rectangle, one array for triangle, etc. So you wouldn't get a polymorphic array as we said before. You mean we could have done student as an abstract class? Yeah, exactly. So now we want to do the same thing for polygon as well. We want to have a polygon array where each element can either be rectangle or triangle, but we want to make sure every one of them statically has the method get area supported. But now in this design, it's not the case, right? Yeah. Yeah, exactly. So now, so what's the conclusion, right? So now, first of all, we say that this does not compile, okay? Does not compile because get area not defined in polygon. Okay, so what does that mean? This means declare get area at the superclass level. Declare area in polygon. But now you're facing a dilemma. You know that you want to put a get area method in the polygon class. However, you don't know how to implement that, right? Because simply what kind of polygon you're talking about. It can be rectangle, it can be triangle, later on hexagon, octagon, right? All kinds of polygons. In that case, the only thing you can do is abstract, signature only. Okay? So in some way, that's a very good question there because we try to see what if you didn't try to do abstract method or abstract class. In that case, you wouldn't have the benefits of polymorphic array like what we had before. Okay? You want to make sure you declare something in the superclass so statically you can still call that method. But because of dynamic binding, once you assign that into different shapes at the runtime, you can call the get area in different version, right? In the different descending classes at the runtime. Okay? Let's see some example. Okay. Okay, that's about polygon. Okay, and then okay, that's by the way, that's what you can do. So you can say polygon is a static type, and then rectangle cannot be dynamic type because every method in rectangle is not defined. Okay, so we're okay. Okay, let's do also triangle, very similar. Okay, for triangle, you can see the only difference is, first of all, we got only 3 sides, right? And then for get area, we just apply the Heron's formula. I'll let you follow that. You know, convince yourself this is really doing the square root formula we had in the slide in the beginning. And then when you have polygon P, the static type, triangle can also be a dynamic type. Again, so triangle is a descending class of polygon, so this compiles. Okay. Questions? Yes.
Previous slide about that abstract get area thing.
Yes.
So my question is, we're doing an abstract so that the static type can access it, but whether or not I have
Yeah,
properly declared it.
Yes, exactly. Let me rephrase what you're trying to say. That's a very good remark. Let me say that again. So now let's go back to the abstract class polygon. The reason that we want to declare this abstract method here is because we want every variable whose static type is actually polygon to be able to call this particular method get area. Because we know that to judge if a method call is valid or not at the compile time, the class must declare that method itself. Otherwise, it wouldn't compile. So after this abstract method declaration here, we can call that. Now, which version is it going to call at the runtime? Now we delegate that to the dynamic binding mechanism. It depends on what the dynamic type is. Remember, the abstract class itself cannot be the dynamic type. Only the concrete descendants can be. In this case, it can be either rectangle or triangle. Okay? It's going to call the corresponding version. Right. Good. Yes?
Why can't we call get address from polygon? Seems like we know that every child is going to be different.
Yeah, again, so if you only put the get area method over here, and also get area over here at this level, that's true. But if you don't declare them in the polygon level, then you wouldn't be able to call that, right? Let's keep. Let's get to this maybe offline. Okay. 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 So now let's just run more examples over here. Okay, now we also got triangle over here. Let's try to have some polygon collector, okay? You can think of polygon collector is a little bit like the student management system, which collects students, right? Let's see how this will work, okay? So now let's say we got polygons and polygon. Line number 2, we are trying to say the array polygons, every element in the array has static type polygon, which means we can assign any objects of dynamic type being either rectangle or triangle, right? At the runtime. It's a polymorphic array. So now let's say we got that. Initial size simply just 10. And then let's add polygon, right? So they like add students, right? So this one I wouldn't go into much detail. And then we can also grow everything, okay? So now you can see that, okay, I'll just, okay, now the dynamic type can be either rectangle or triangle, as we said before. Let's try, this one is a bit more tricky. How about this one here? So this one is just a polygon collector. Let's say we got something a polygon constructor, okay? Let's see how this one is gonna work. Now, let's say we have get polygon over here, okay? And then you can see that it's gonna take an array of sides. So now this is the idea. You can see the return type for polygon here is, for get polygon here is just polygon. Right? So what can we return as an object? It can be either any of the descendant classes of polygon. It can be rectangle, it can be triangle. Let's try that. So now we simply say the return value is going to be a polygon. Okay? So what can be on the right-hand side? It can be either rectangle or triangle, right? Descendant classes. Okay, let's see how we do this. Now we say that if the arguments you give to me has length 3, that means you want to create a polygon with length 3. In that case, I'm going to give you a triangle. Okay? Now you can see that why does this line number 5, why does it compile? Because triangle over here is a descendant class of polygon over here in line number 3. Okay? Similarly, if the sides.length is equal to 4, that means we want to create a polygon of size 4, of 4 sides. In that case, I'll give you a rectangle. You can see that the dynamic type of the object you actually return from this method can either be triangle or rectangle, right? Okay, and then return. Okay. Okay, you can just go over these. So just about polymorphism and dynamic binding. Okay, let's do a test very quickly. Okay, tester. Okay, so now first of all, you can see that we got polygon over here. Okay, the static type of P is polygon. And then we say that P is assigned to a new dynamic type, rectangle. This one compiles. And then we can simply try to say P dot get parameter and P dot get area. Now, I want to remind you very quickly. Now, you can figure out why the output value is to be 14 and 12. It's very easy to see. But when I say P dot get parameter, which version am I trying to call? So which class did we define the get parameter? Polygon, right? That's shared, right? Good. What about get area here? Depends on the dynamic type, right? In this case, rectangle. Okay? So now this is going to call the rectangle get area, which is going to be 3 times 4. Okay? Easy. And then let's try to reassign P to be a new dynamic type. So now it changes to triangle. Now you can see that, so that's polymorphism, right? You can change the shape. And then if you try to say get parameter again, so now which version of get parameter is it going to call? The same version, no, get parameter. The same version, right, in the polygon, right? But get area, you're right, that will be the triangle version, okay? So that's just a very easy check. Now, this one here, polygon collector. Let's see that collector over here. Now, you can see that I can say add polygon and add polygon. I add basically rectangle and triangle, pretty much like I say SMS dot add resident students and add non-resident students. It's polymorphic, okay? So now, let's say after 12 and 13, if I say this, look at line number 14. I say that collector.polygons at position 0 is polymorphic, right? So now I say get parameter over here. Actually, this one is not that exciting. I'll show you the next one. Let's just change this a little bit. If I put get area over here, okay, I'll change that. Maybe that's more interesting to see. Now, if I say get area in line number 14, which version is it going to call? Rectangle, right? Because rectangle is the first one, pretty much like it will be the resident students, right? In the previous case. And line number 15, you'll be triangle. Okay, good. You get it. Okay, now constructor, the last test. Okay, just give me 1 minute. We'll finish very quickly. So now let's say we got an array of 4 sides. And then we simply pass these 4 sides into get polygon. So what is it going to do? It's going to return a rectangle back to me, right? Just see the previous method definition over here. You can see that if the number of sides is actually equal to 4, I'm going to give you a rectangle, okay? That's something you should really see. Okay, you get a polygon over here. Now, when you say P instance of polygon, true or false? What's dynamic type? So after line number 2, what's the dynamic type for P? Rectangle, right? Because we got the size of the array is 4, okay? So now, instance of, so the dynamic type is rectangle. Rectangle is a descending class of polygon, so true. What about here? Rectangle, dynamic type, descending class of rectangle, true. What about this? False, right? Okay, good, very easy to see. Okay, you can try to call the method, and then the get area is going to be the version in rectangle. Okay, similarly, if I try to do another double array, 3, 4, and 5, 3 sides. So now, what's going to be the dynamic type after line number 11? Triangle, right? Because it's going to return. It's a different branch. And then, if you try to do instance of polygon, true. Instance of rectangle, false, very good, because triangle is not a descending class of rectangle. And this one's true. Okay, you got it. Okay, this one here simply summarizes the abstract classes. I will start from here on 30.